to the first session on ionic equilibria. In this session, we will be dealing with the dissociation of electrolytes in solvents as well as the theories regarding the dissociation of electrolytes and what happens to the electrolytes when they get dissociated in the solution. And dissociation of the electrolytes into ions, you can take an example, that is CH3 COONA, which is an electrolyte which dissociates into its ions like CH3 COO minus plus Na plus ions. So, you are getting two ions, one is a cation and the other one is an anion. Now, when we come to the electrolytes, we all know that there are two categories of electrolytes, that is strong electrolytes and weak electrolytes. An electrolyte which is completely ionized in solution, we call that to be a strong electrolyte, and which is only partially ionized, we call that to be a weak electrolyte. For example, if I take sodium chloride, you cannot write an equilibrium, it is completely dissociated into Na plus Cl minus ions. While in the case of sodium acetate, or if I take acetic acid, you have to put in equilibrium arrow, that is a forward and backward reactions in which we have an equilibrium existing between the ions of acetate ions and H plus ions, which is actually generally written as H3O plus ions, because that will be hydrated. Now, here this is not a complete dissociation in this case. So, we call acetic acid to be a weak electrolyte, while sodium chloride, which is 100% ionized, we call that to be a strong electrolyte. Now, let us see what are the theories that are based on explaining these behavior of electrolytes. First one is the Arrhenius theory. Arrhenius has been conducting many experiments on electrolytes, and he found that all electrolytes, they conduct electricity and also they show abnormal colligative properties. In order to explain these properties, Arrhenius proposed the Arrhenius theory, and some of its points are discussed here. The main points, first one is, when an electrolyte is dissolved in water, the electrolytes dissociate into electrically charged particles, that is, they will be carrying charges. They are known as ions in such a way that when you take the total charge of the positive charge ions and the negative charge ions, that will get cancelled and it becomes 0, or you can say that electrolyte will be neutral. So, the number of positive ions produced will be equal to number of negative ions produced from an electrolyte. Now, at a particular concentration, there will be a particular amount of electrolyte ionized. Now, how does this ionization take place? It depends upon certain factors like nature of the substance, concentration of the solution, and also on the temperature. And the extent of ionization always varies with concentration, and on increasing the dilution, or if you keep on adding the solvent, the solution goes on diluted and the ionization increases. So, it goes on increasing and reaches a maximum value, further which if you keep on diluting, the value does not increase. So, on dilution it keeps on increases and reaches a maximum value. Third point is, the ions formed from the partial dissociation will be in an equilibrium, and that too a dynamic equilibrium with the unionized molecules or species. You can take, that is the first thing I have discussed about acetic acid. This time I will take a weak base, let it be ammonium hydroxide. Okay. And ammonium hydroxide ionizes to give ammonium ions plus OH minus ions. And these two ions, that is the ammonium ions as well as the hydroxyl ions, they are in dynamic equilibrium with ammonium hydroxide, which is in the undissociated form. That is what the third point says. Next is, that is the fourth point, the ions are free to move in the solution independent of the other when an electric field is applied. The positive ions go to the negative pole and the negative ions goes to the positive pole. Now, here, that is, when current is passed, you have both negative and positive poles, or you can call it as the electrodes, negative electrode and positive electrodes, and this negative electrode will be usually a cathode and positive will be an anode in the case of an electrolysis. It is not always like that, but in the case of electrolytes it is true. And the conductance of current through the electrolyte is due to the movement of ions through the solution, and greater the ionization will have more of ions and greater will be the conductance of electricity. Fifth point is the properties of electrolytes in a solution. They are the properties of the ions that is being furnished or dissociated from that electrolyte. An ion acts as an unionized molecule, that is very important. That is, an ion acts as an unionized molecule means, like if I am dissolving sodium chloride in water, that will be completely ionized as Na plus and Cl minus. They are independent species and they will be acting as unionized molecule with respect to colligative properties, because colligative properties are properties that depend upon number of particles in a solution. Now, if I take any organic molecule, like if I am taking urea, this does not get ionized. So, urea, if you take 10 particles, you will be getting 10 particles and that will be contributing towards the colligative property. While if I take an electrolyte, the case is different, because I have taken only some 10 molecules of sodium chloride, I assume, and then you will be having, this is only, I have taken 10 molecules, not moles, I am saying molecules, and this 10 molecules will give you 10 sodium ions and 10 chloride ions, and that makes a total of 10 plus 10, 20 particles. Now, what happens here? The colligative property measured will be double, because the particles has been doubled. So, that is what it is said here, that is, they act as unionized molecules with respect to their colligative properties. Next, let us see what are the limitations of Arrhenius theory. Strong electrolytes are completely dissociate even at high concentrations. We need not dilute the solution, it is already ionized, and therefore, there are no chance for an ionic equilibrium, like what I have told you before. When I take a strong electrolyte, I will give the complete ionization. When I take a weak electrolyte, for example, let it be ammonium hydroxide itself, the dissociation is not complete and you will be having ammonium ions plus hydroxyl ions along with ammonium hydroxide, which is undissociated, and there exists an equilibrium, and this is possible only when the electrolyte is a weak electrolyte. If it is a strong electrolyte, the case does not arise, because when you add sodium chloride, it is naturally 100% Na plus ions and chloride ions. So, this leads to the failure of concept of degree of ionization in the case of strong electrolyte. That is one of the weakness of Arrhenius theory. Second is, it does not consider the inter-ionic attractions between the ions, because as you can see that when an electrolyte is diluted, its conductance increases normally, as we have seen in previous sessions. Now, when the conductance is increasing, it is not because number of ions are increasing in the case of a strong electrolyte, it is because the inter-ionic force of attractions are reduced. And Arrhenius theory does not consider about the inter-ionic attraction between the ions. So, again that is also another limitation of Arrhenius theory, and again it could not explain the variation of transport numbers with concentration. So, these are the limitations of Arrhenius theory. Now, we will go to the next one, which is known as Ostwald's dilution law. And Ostwald's dilution law is, it is considering the dynamic equilibrium between the unionized and ionized molecules in an electrolyte solution, and we are going to apply the law of chemical equilibrium to this theory, and we derive a mathematical expression which is known as Ostwald's dilution law. And again you should remember, since we have this equilibrium between the ionized and unionized molecules only in weak electrolytes, so Ostwald's dilution law is applicable only to weak electrolytes and nothing for a strong electrolyte. So, this gives an explanation for weak electrolytes. Now, let us go. That is Ostwald's dilution law, it is a mathematical expression derived by Ostwald by applying law of chemical equilibrium to Arrhenius theory. So, he is taking the concepts of Arrhenius theory itself and applying the law of chemical equilibrium to that. Okay. Now, let us see how it is done. Here I have taken an electrolyte AB, which is a weak electrolyte, which ionizes as A plus and B minus as cation and anion. Now, let us assume I have taken C moles per liter of AB, that is the weak electrolyte, and I have put that in a solvent. Let us consider that to be water. I put AB in water and AB gets ionized into A plus and B minus ion, not 100%, but to certain extent. Now, what I am going to assume is that I am taking degree of ionization as alpha. Now, what is degree of ionization? It is a fraction of total number of molecules that has been ionized. So, that is degree of ionization, or you can say that it is number of moles ionized per 1 mole. Okay. Now, if alpha is the degree of dissociation, for 1 mole alpha is getting dissociated. Okay. So, if C moles are there, okay, if it is 1 mole you will get alpha. Okay. Now, here what we are going to do is, suppose we are taking 1 mole, the undissociated will be 1 minus alpha. If I am taking 1 mole undissociated per mole, I can put it like that, that is equal to 1 minus alpha, because alpha has been dissociated, because alpha is the degree of dissociation. So, remaining will be 1 minus alpha. I have taken C moles and therefore, that will be C into 1 minus alpha. And here we can see that from 1 mole you get 1 mole of A plus ions, and therefore, if I am taking C plus, I will be getting C alpha moles of A plus and C alpha moles of B minus C. That is the case, because with 1 mole I will get 1 mole of A plus, 1 mole of B minus. If I am taking C moles, I will be getting alpha is the degree of dissociation for 1 mole, for C moles that will be C alpha and C alpha. Next step, we are going to apply the chemical equilibrium to this. According to chemical equilibrium, the equilibrium constant K will be equal to molar concentration of products multiplied by the other product B minus, whole divided by the molar concentration of the reactant. So, this is the reactant part and these are the product parts. And here we have written the molar concentrations here, that is C alpha divided by C into 1 minus alpha. 1 C gets cancelled. So, in the next step, that will be equal to C alpha square divided by 1 minus alpha, and that is the equilibrium constant. Okay. Now, what we are going to assume is that, let us consider alpha being very small, because this is a weak electrolyte, the ionization will be very little and therefore, alpha will be very small. Now, if alpha is very small, 1 minus alpha, it is a very small fraction, and therefore, 1 minus alpha can be approximated to 1 itself, like that will be 0.0001. So, 1 minus 0.001 will be 0.999, and that can be approximated as 1. So, again this expression takes the form k is equal to C alpha square, because the denominator becomes 1, okay, or alpha is equal to square root of k, and C comes over this side, k by C, and this expression we call it as Ostwald's dilution law for an electrolyte. You can take it for any case. If I am taking it for an acid, we will put it as alpha is equal to root of that k will be the dissociation constant of an acid divided by C. If I am taking it for a weak base, alpha is equal to square root of Kb by C, which we will be seeing in detail later. So, one thing you can see that C is in the denominator, which means that if C increases, what happens? Concentration increases, alpha, the degree of dissociation, decreases. That is, you won't be getting much of ions in concentrated solution. As we go on diluting, that is, C goes on decreasing, concentration decreases on dilution, and the value of alpha increases. Now, let us see what are the limitations. Ostwald's dilution law applies only to weak electrolyte, which I have already mentioned, because only in the case of weak electrolyte you have an equilibrium between the ionized and unionized molecules. In the case of strong electrolytes, even in very concentrated solutions, they are completely ionized, and by adding solvent there is no increasing number of ions. So, you can't say that is number of ions are increasing, and therefore, this law is not applicable for the strong electrolytes which are completely ionized. Next, let us go for a problem based on the Ostwald's dilution law. Now, here the problem goes like this: calculate the degree of ionization of 0.1 molar solution of a weak acid Ha at 298 Kelvin. And given that Ka stands for the dissociation constant of an acid, that is similar to an equilibrium constant, which is equal to 4.9 into 10 to the power minus 8. So, let us see what are the data we have. We have the concentration, that is equal to 0.1 molar, and temperature 298 Kelvin, and we have got the ionization constant of the acid 4.9 into 10 to the power minus 8. Okay. Now, first thing what we have to do is we have to write the dissociation of the acid, only then you can say that the equation is proper or not. So, here they have given the weak acid as Ha. Ha means that is equal to, that gives dissociates into H plus A minus, that is for easier way, and actually it is considered that H plus being a proton, it cannot associate itself alone, and therefore, it goes on getting hydrated with number of water molecules, and it can be different. For simplicity's sake, we take only one molecule of water. So, actually this can be written as Ha plus H2O gives H3O, because this is an exposed proton, H3O plus which is being hydrated plus A minus, that is water takes up a proton from this and gets hydrated to form H3O plus A minus. Now, in this case the equilibrium constant can be written as K is equal to concentration of H3O plus into concentration of A minus whole divided by concentration of Ha into concentration of water. But we all know that water is present in excess, and therefore, the concentration of water can be taken as a constant. So, I am taking water to this constant, equilibrium constant, I am going to take it to that side. So, I have K into concentration of H2O, which is another constant, and this constant is taken as Ka, which is the dissociation constant of an acid. So, Ka is equal to H3O plus into concentration of A minus divided by concentration of H. The value of H is given. Ka is equal to 4.9 into 10 to the power minus 8. Now, you can see here that the concentration is 0.1 molar, and you have to find out the degree of dissociation alpha. Okay. So, you have to write an expression for this first, that is, if again I am going to consider that as C moles, put it as C moles, okay. Starting you do not have anything else, and again here this will be C into 1 minus alpha if alpha is the degree of dissociation, and this will be C alpha, this again will be C alpha as we have discussed above, and therefore, the equilibrium constant Ka is equal to concentration of H3O plus, that is C alpha here, concentration of A minus, again that is C alpha, whole divided by concentration of C into, that is HA, C into 1 minus alpha. Okay, the C and C gets cancelled. You get the same expression, Ka is equal to C alpha square. Again, taking alpha to be very small, you approximate that to 1. That this becomes C alpha square, and alpha will be square root of Ka by C. Ka is given square root of 4.9 into 10 to the power minus 8 whole divided by 0.1, that is the concentration, and if you calculate it, the value comes to 7 into 10 to the power minus 4. Hope it is clear. So, in this session we have been seeing with the dissociation of electrolytes, how it takes place in a solvent, and two theories, one is Arrhenius theory and the other one is Ostwald's dilution theory. In Arrhenius theory, it is actually a theory which explains mostly the characteristics of a weak electrolyte, and Ostwald's dilution law, it is a law which is based on Arrhenius theory itself. So, that is also applicable only in the case of weak electrolytes, and we assume an equilibrium existing between unionized molecules and ionized molecules, to which we apply the chemical equilibrium concept and we get an Ostwald's dilution law expression. Thank you.